Hello and welcome to Module 8, the Six Sigma Approach. Today we will talk about measurement system analysis. Measurement systems analysis is essential to assure data integrity, select proper gauging for making measurements, and to quantify variability due to the measurement system. The most common tool for this is what's called a gauge R&R. This is used to analyze variability of the measurement gauge and the operator, and the R stands for repeatability and other R stands for reproducibility. Essentially, repeatability would be if one person measures the part several times, how consistent would their results be? Reproducibility would be if one person measures it and then another person measures it and another person measures it, how consistent is it from person to person? Excessive measurement variability is a problem and can cause massive repercussions. The most obvious problem is that you can have an out-of-specification product that would be accepted because of measurement inability to catch it. The other issue that could happen is a part or product that is within specifications could be rejected and reworked and not given to the final customer. Lastly, part-to-part variability is not detected and continuous improvement efforts are hindered. If you cannot go and measure it to the extent that you need, then you can't truly evaluate how it is performing and manage it or understand how you could improve it. Measurement systems analysis can be used for both variable or attribute data. Although variable data is probably more common in manufacturing, service industries typically will use more attribute data. It can be used for non-destructive or destructive testing, although non-destructive is much more common. An example of a destructive test might be if you go to check the adhesion of a sealant. You have to, in order to check how strong it adheres, you have to actually destroy the sample because you have to pull the product until it's failed. Once it's failed, you obviously can't go and remeasure it, so it's impossible to go and measure the same product twice. There are tools and techniques to evaluate how to handle those destructive types of tests, but typically speaking, those are the exceptions rather than the norms. When doing a gauge R&R study as a fundamental component of measurement systems analysis, you have to look at what your measurement should or should not be. So first of all, measurements should be precise and accurate, in which case the measurement method or the device does not vary much from the actual value. The typical problem here is inaccuracy or bias, in which case the measurement method or device results in values that vary greatly from the actual value. Measurement should be repeatable in that the repeated measurements of the same item or characteristic by the same person would yield the same result. In reality, the typical problem is that they're not, and that repeated measurements on the same item or characteristic lead to inconsistent results. They should be reproducible, so that two or more people measuring the same characteristic and using the same methods should get the same result. The typical problem there is that that is not the case, and that multiple people measuring the same characteristic in the same way will not get the same results. And they should be stable over time, in that the measurement system does not change. Unfortunately, that is not the case, where measurements taken will drift and change over time based on the variability of the gauge, the calibration of the gauge, or things as well. These are all typical problems that impact the capability of measurement systems and add to variability within the measurement process. So gauge variability can be reduced into four primary categories. First of all, repeatability, which is the variation of the gauge when used by one operator over a period of time. The calibration, which is the gauge accuracy. Stability, which is the gauge does not change over time. And then linearity, where the gauge does not differ in accuracy at high or low values. When you look at overall variability, you start at the very top and say, here's what your observed measurement are. Regardless of your measurement system, you have an ultimate output. From there, you have components for either the true values or the measurement error. The measurement error can be broken down into multiple categories: the bias, the gauge R&R, the stability, and the linearity. Furthermore, you can take that gauge R&R and you look at both repeatability and reproducibility. The reproducibility, being from person to person, could be from within a specific person. So just switching one operator to another operator will give multiple values. Or it could also be operator to part. So for example, when you have 10 operators measuring this part, you get very consistent results. However, this next part, when you have 10 operators measuring it, they get very inconsistent results from part to part. The basic model of precision looks at both reproducibility and repeatability in a linear fashion, and they do build upon each other. It is a squared relationship. Measurement system variation is equal to the variation due to the repeatability plus the variation due to the reproducibility. So typically you take the squared value of both of them, combine them together, and take the square root, and that gives you your overall R&R, gauge R&R value. This represents the most common cause measurement within the measurement system. By common cause, this means this is going to be the day-to-day measurement that can be inherent to the process and can be expected on an ongoing basis. So let's look more at repeatability. So repeatability is essentially the inherent variation of your measurement system. This will occur when successive measurements are made under the same conditions. In order to evaluate this, you should use the same part, same characteristic, same person, same instrument, setup, and same environmental conditions. If you were to do the same thing over and over again, how consistent would those results be? That would be your repeatability error. Conversely, reproducibility is the variation on the average of measurements made by different operators, measuring the same characteristic on the same part, the same measurement instrument. How consistent is operator A to operator B to operator C, and that is reproducibility error. The total gauge R&R is considered the total standard deviation squared of the measurement system divided by the standard deviation squared of the observed values times 100, and that gets you your R&R value. Typically speaking, less than 10% is considered acceptable or, if not excellent, variability, and less than 30% is a tolerable standard. This also may vary significantly based on the particular application, the cost of the gauging, or just the risk involved to having measurement error. In order to do a gauge R&R study, the first thing you do is have to simulate the real-world conditions as closely as possible. So use the same people, parts, procedures, etc. that you would typically be done in production. A common flaw I see in conducting gauge R&R studies is when they're done in lab conditions as opposed to production conditions, or they're done with engineers or technicians as opposed to production operators who are using the measurements on a daily basis. It's important to use whatever is truly going to be representative of your measurement system, because that is how you're going to evaluate it. As a general rule of thumb, you would want to evaluate a minimum of 3 different operators to truly understand reproducibility error. You'd also want to evaluate at least 10 parts and reevaluate each of those 10 parts a minimum of 3 times in order. That way you can evaluate how consistent are people from measuring the same part multiple times. It's important to follow the gauge discrimination level of the 1 to 10 rule. And the 1 to 10 rule states that your gauge should be able to discriminate at least 10-fold better than the tolerance that you are trying to measure to. So if your tolerance is plus or minus an inch, you should be able to have a gauge that can measure plus or minus 1/10 of an inch. The gauges should always be calibrated prior to conducting any measurement systems analysis. And then avoid potential for bias. It's important to randomize replications. People will want to give good results and will unintentionally look at a part and try to remember what it was that they gave the result last time so that they can give the same result this time. You don't want to put that bias into place, so you want to randomize the parts so that operators don't know which one it is, and that you don't have any bias stimulated from the parts that were measured first, that parts were measured last based on the measurement system. It is also important not to coach participants. Participants should be trained in how to use the gauge, but you cannot give them advice on how to measure the part or how other people have measured the part. The point is to see how consistent they are and observe those values without trying to give them advice and trying to inherently inject bias into your system. Again, you are trying to use this study to evaluate what is truly reflective of actual technology of your actual measurement system. So in those steps, first of all, start with ensuring that the gauge is calibrated and that the operators are trained. It's typically good to make sure that you pick operators who are fairly well experienced, but try not to cherry pick your most experienced operators. You can, just like anything else, want them to be representative of the type of person who will be measuring these parts. The first operator will measure all the samples in random order, and then the additional operators will measure all the samples in random order. And then you repeat those steps multiple times until everybody has measured all the parts multiple times. From there, you evaluate the statistics of the measurement system effectiveness. For the purposes of this class, I'm not going to get into the statistical measures, but I encourage you to take one of the quality courses available in the IMSC department, where they spend more time in measurement system analysis and actually walk you through some examples of conducting gauge R&R studies. This is an example of a gauge R&R study that might be conducted and the results that you might attain. The chart on the left shows a summary table that in this case was taken from Minitab, or a statistical software. It starts by showing the total gauge R&R and then breaks down the repeatability and reproducibility error. It then kind of shows the part-to-part variability so that you can compare the measurement system variation to the part-to-part variation and get a total percentage. The chart on the table on the right shows graphical outputs in here and shows 6 graphs that come with the parts. By and large, you want your variability to be part-to-part. The more of your variability that is part-to-part, the less of your variability is related to your measurement system. The first graph in the upper left shows the components of variation and shows that in this particular study, that is exactly what happened. The second chart on the right shows the result readings in time series order. In theory, the closer that they are grouped with each specific part, the more reliable the measurement system is. The R chart and X bar chart show the special causes. The R chart should be stable and in control limits, which it is, whereas the X bar chart should not be stable because you want variability to be due to part variation, not measurement systems. And the total firm to read by operator should be spread out to show that neither one of the 3 operators selected had higher or lower values overall. And then the operator-part interaction over in time series, just like the total part interaction, should be closely grouped together in time series. So once you are done completing the study, you then have to evaluate the results. And the question oftentimes comes up with, what if the results are unacceptable? Well, the first thing is to determine why the source of the results and why were they unacceptable. Are they due to repeatability, or are they due to reproducibility, or both? The result may tell you what you want to know. So it could be that the device or operators or both are not doing the job, and then that drives you to the direction of where you have to take corrective action. The best ways to fix it will depend upon what sources of variability you have. If you have repeatability errors, you should look at maybe you have a poor measurement device, and you should look at maybe you should get something with a little bit better precision. If you have reproducibility, that's typically a case where people are using different techniques, and the first step there is to look and evaluate your training and standardize your work procedures. If that's ineffective, another key option there is to limit the number of people conducting measurements. Obviously, if you only have one person conducting measurements, you're not going to have person-to-person error. There are certain challenges associated with doing this in terms of maintaining it in production, but this is a very effective way to eliminate reproducibility error. And then also just look at any specific differences and see if there were any observations during the study that might have contributed to this error.